Aloha, everybody. I sounded very American when I said that, didn't I? Very Virginian. So, look, hey, I'm honored to be here to do a favor for Ehab. Ehab and I met several years ago, and it's nice to see some familiar faces coming back here. Also, Ben Daxon and I got to meet a few years ago. I knew right away he was the black sheep of Mayo Clinic because he loved APRV, and I'm also black sheep. I love APRV. So it's nice to see a lot of APRV talk here. But this is not going to be about APRV. This is essentially going to be me, David from Virginia, a registered respiratory therapist that's worked with every ventilator and every patient on there. And basically, instead of going too detailed into a lot of respiratory mechanics because we're abbreviated on time, one of the growing trends that you see in the market is simulation training. So how many of you have had the ability to download a form of a mechanical ventilator simulator and actually use it for training purposes? Anybody in this room? Okay. So okay, what we're going to do is the Hamilton Medical Vent Trainer app is the newest one that's open on the market and for public download by anybody in this room. So go to your app stores and you can download it for free. But unfortunately, we've had to resort back to an older simulator for today's discussion. So for those, again, the content and the context of today is how to ease your learning and how to improve your learning recall through simulation. All right, now how many of you have missed out on training opportunities because you couldn't get a ventilator into the room to provide the training? All of us have. In order to train on a ventilator, one must have a ventilator in the room, correct? Well, what do you do when you don't have a ventilator to train on? Luckily, there's been simulations that have been designed so that what it does, it's set up in order for you to have the ability of the tactile experience of putting the settings in, changing the conditions, and that way it enhances your learning and your recall when you go actually to a ventilator. So looking at this, and just to keep this kind of simple for everybody, this is an older version of a simulator, but the concepts are still the same. How do we take the real devices in real life and build it into a simulator so you're not reliant on the device to be beside you when it comes to training? Can you do this on your iPhone, your iPad, and on a laptop? And the answer is absolutely yes. All right, so what we're going to look at is a couple of different things. Now, how many of you, when you've ever taught a class, just raise your hands if you've ever taught mechanical ventilation to students, new hires, all that stuff. Okay, how many of you were unable to get the test lung to cooperate and show what you wanted it to see on the screen? Raise your hands. Okay, good. That's a problem. Me too, guys and girls. So this happens. What simulators do is they clean all of that up. So I'm not reliant on a test lung to create, let's say, a pressure volume curve or an asynchrony. Now, certain simulators, if you just look and you get the option of going to a particular simulator here, you can click on, oh, it's not opening up. So again, this session will be coupled with what do problematic simulators look like on a computer? Yes, I agree with what that guy just said. Okay, so look, all right, when simulators work, they look like this, and when they don't work, this is what they look like as well. Yeah, am I doing something incorrect here with this? Nope, I'm drawing on it now.
I know. So we should do it from here. So
okay, here we go. We got full screen. See, look.
Yeah.
And when the operator of the simulator doesn't know what he's doing, you call on a good friend from Hawaii. Give him a round of applause for Ehab. This is comedy hour as well, too, just to eat up some time. All right, so look, again, when you're dealing with a test lung showing mechanics changes, you have to physically do this with your hands. This is problematic. You may not have the right test lung, but in certain simulators, you have the ability here. So what I want you to do is just draw attention to what the waveforms look like in this particular mode. So the default mode on the simulator is ASV. We typically show this in volume control, but what I want to show is just changes that occur to the waveform by virtue of you mechanically operating the changes in the mechanical properties of the lung. So right now we're looking at a healthy patient that's got a compliance of 64. You're doing a training session on ARDS, so you obviously would lower this setting to show a reduction in compliance. Now the goal to show the reduction in compliance is so that you show the change in the waveforms associated with that, okay? We all know numbers. We can all walk to a vent and go, all right, a compliance of 60 down to 30 is a bad thing. But what does that mean from a patient-ventilator interaction? What are the waveform changes that occur? Now, what you probably didn't take note of was the flow time pattern is one thing that changed right away. So in a normal healthy lung, it'll take a decent while for the lungs to fill, and you'll see this flow time pattern take its time going down to baseline. But because we've reduced the compliance, that flow ends up filling up the lungs much sooner. So there was a truncation of the inspiratory flow pattern, which was indicative of a reduction in static compliance. You are also witnessing in this particular mode, as a reduction in that compliance, an increase in driving pressure associated with the ASV mode. So how many people here are familiar with the Hamilton ventilators and have used ASV mode? So we have a handful. I know Ron's had a long career of utilizing this and is one of my personal ASV experts as well. But again, you using the simulator, you can quickly teach somebody, hey, when the compliance does this, you can expect the response of the scalar waveforms to look like this. Ron did not need to go grab a ventilator or have one transported to EHAB's conference for that particular reason. Same deal here. You got the compliance, you've got the resistance. We all know what that looks like. I'm going to change certain parameters. But again, this is just to give you some encouragement that if you get your hands on a simulator, you can feel confident that manipulating the dials inside the simulator will produce some of the physiologic realities associated with what's on the screen. Okay, you have anything else you wanted to kind of show with this?
We can actually switch to maybe
Go
so
ahead.
as we can measure the peaks and plateaus and whatever. Just go with the volume.
Okay.
Just show different modes.
Yeah, see, we're doing this together. We planned this out like well in advance. So there's nothing better than like informal partnership up on the stage.
Yeah,
All good. Oh, the infamous square flow pattern. You're going that direction. Okay.
Yeah, I just saw see like the peaks and the plateaus and stuff.
Absolutely. So what he wanted to show was the ability to, again, you're training somebody on how to do an inspiratory hold or an expiratory hold to determine auto peak and plateau pressure levels can be done through the simulator as well. So if you're not familiar with the Hamilton vents, it's fine. Each of the ventilators out on the market have the ability to do an inspiratory hold. In this situation, we can see that the peak airway pressure is 29, but let's say that that's not so clinically relevant for what I'm looking at. I want to know the intraalveolar pressure. So I want to know the plateau pressure. So let's just go under the tool screen here. Oh, it's not going to do it. So that was interesting dynamic that we showed you is what we thought the simulator would do. It's not doing. So we can't do the inspiratory hold in this simulator. So
yeah, I'm sorry about that, my mistake. But what we can do is we can go to the controls and put a hold.
there you go.
I think it should work. Let's try it. Oops. Okay, so it's not a total hold. The hold needs to be like a couple of seconds, but at least it gives you an idea of like peaks.
Yeah, good. But again, real quick, something changes with your teaching strategy. You can modify the simulator with a different approach. So putting an inspiratory hold on a breath, which this is a practice that's commonly done outside the United States. You see this all over Europe where they just put inspiratory holds on so they can routinely monitor plateau pressure. But in this situation, if you're concerned about the intraalveolar pressure, you can see that the peak airway pressure is 30, which might cause some concern based off of your ventilation practices. But the real plateau pressure is a fraction of that. And this plateauing inspiratory hold that you see here, if you draw it back to the y-axis, it's somewhere around 21. So if you were clinically concerned in this situation that your peak airway pressure was high, you have the ability through a simulator to put an inspiratory hold on and say, hey, look, actually it's not. And through this simulator, I hate when my devices go off like your laptop does. It happens to all of us. That's why we're not sitting in judgment. But that's a good point that EHAB brings up is you can do certain ventilation practices like this to continuously monitor respiratory mechanics as well. And again, trying to make sure we stay on time and provide the last presenter and lecturer the ample amount of time going forward. If you look and see, you have the ability for the changes on the ventilators that you would want to see. And in this situation, you can click on each of these scalar wave patterns and you can change the screen to what you want to see. And then the newer simulators, you have the ability for the intelligent panels to pop up. So complete configurability associated with this. In the passive patient, so we're going to move on and look at some of the advanced mechanics, but One of the most difficult things to do with ventilators is to show how a single pressure volume curve breath is delivered to assess lung recruitability and potential for high peak. And if you've never had any practice with this, we'll just show you real quick what this looks like on a simulator. So over here on this side is the y-axis, which is volume, and on the x-axis, which is pressure. And depending on the ventilator that you're using, you can have the ability to provide one single, very slow flow breath that goes through the respiratory system. And the pressure volume relationship that it maps out can tell you, is this a patient that's highly recruitable? Can they benefit from high peak? Can they benefit from APRV, since that's been a discussion point of this conference? Should we avoid peak? And so what you see here is the ability to configure certain parameters. Where do you start the breath at which pressure? I'm going to leave this pressure at 5. The ramp speed is just how fast we're going to do it. And to save time today, I'm just going to leave this sitting here at 3. The recruiting pressure. What is the top airway pressure I want to go to during the single breath maneuver so I get a complete picture of the pulmonary mechanics? And so the typical CT analysis that's looked at ARDS has shown that you typically get a general high level of recruitment at a pressure of 40. So I'm just going to put this at 40. I'm not going to do a pause, and the end people will just leave at 5. So what I'm going to do is I'm just going to hit start, stop, and the automation occurs. All right. The good thing with the simulator is that this is what it looks like on the real life ventilator. All right. So you can see the pressure going up here. So it's a nice slow flow breath. It's a single inflation. And what's going to happen is the curve here is going to populate and show us whether or not this patient can tolerate high PEEP or not. For reference points and without a slideshow behind me, the fatter this curve looks, the more of a football, like NFL football, pigskin. You guys know that. So the fatter this curve looks, the more highly recruitable this lung is, the more opportune or more beneficial higher PEEP recruitment maneuvers, and again, modes like APRV would be. So in this curve, without diving too far into it, the area within the curve is measured as hysteresis. And so that's just saying that's all the volume and pressure relationships taking place. With this one curve, which I would have to grab a ventilator and a test lung and manipulate it with my hands. And anybody that works in industry with mechanical ventilators can tell you it's very difficult to demonstrate a real life curve manually doing it with your hands. You can use the computer software to actually simulate what one looks like. And to kind of bypass all of this and again, stay on time, looking at the curves for my entire career, I can sit there and say that this lung shows a high recruitment potential. So I could take the picture of this curve, run back to my physician and say, guess what? I like the idea of APRV. This person shows signs that their lung can handle high pressure. And from that one curve, I have an idea of whether or not there's going to be a significant safety profile of high or low PEEP with this patient. Is there anything else you wanted to point out about the PV curve, or just?
No, I think that's you. Sorry, you mentioned the hysteresis, and that's actually most of the time how we.
It doesn't like you.
Oh, okay. That's how we usually like set it at the maximum hysteresis. It's okay. You can some people also look at the low inflection point. This part here, sorry, if you're gonna use APRV and the top pressure, you can see it's beaking. So that's probably, you shouldn't exceed pressure than here. There is other stuff which I know they didn't put the pause, but if you see the pause and you calculate the area of the maximum hysteresis to the change of volume when you put the pause at the end, and usually it's called NMD. And if that ratio is more than 41, studies show that this lung is recruitable. But that's the only thing I want to.
Good. Yeah, thank you. I appreciate that. So far, we've lost the microphone, but I'm a loud person, as you've already can tell, so I know y'all can hear me in the back. So moving on for just a couple of additional things, and again, to stay on time for the last presenter. If you look at the simulator, I used to be in a cover band, so I'm very comfortable holding a mic like this. And if you're ever doing karaoke or you're in a live band, do not cup the mic like this. A lot of rappers do that. I like rap music, but you see how distorted I sound? This is much better. That's your lesson for today, ladies and gentlemen. Okay, look, to kind of wrap this up too, when you're teaching with the device, depending on the test lung you have, we talk about the different mechanics you have now. you may think in your head as you're presenting something, I say, I want to show a compliance of this and resistance of this, but there's also presets. So if you look at this particular simulator, there's a couple of additional functions that are very difficult to show while you are training on a device. Now, if you see here, what we have is two particular things that show a patient rate. That's good. That's spontaneous rate, and a patient effort. So in this situation, you have a rate set of 15. Okay, you may want to demonstrate to your new hire at the bedside, what does it look like when the patient engages in active ventilation? What does it look like when their muscle pressure changes? So in this situation here, if you wanted to show somebody on full ventilation of SCMV and that they're actually starting to wake up from sedation and breathe more on their own, you can simply just go over and change the respiratory rate of the patient. Now, what I'm going to do is I'm going to dial the rate higher than what is the set rate. So in this situation, I'm going to put the rate at around 22, 23. And what we should see, all right, you can see the changes in the waveforms, which most of the time you may not be able to showcase this with the patient, but now what we're seeing is patient activation through the simulator. So this is a patient-generated breath. This is a passive ventilated breath. Here's also another patient-generated breath. And what I want you to pay attention to, which you may not be able to show with the test lung when you're teaching, is the change in trajectories of the pressure time curve. So this mandatory breath is showing a pretty linear relationship of pressure over time, which means the lung is passively ventilated. There's no muscle pressure that's actually active during the situation. But when the patient triggers the breath and they're breathing on their own, they're starting to create this kind of a contour to the pressure time curve, which means there's a degree of muscle pressure during inspiration that is higher than the ventilator pressure. And this term culturally is referred to as scooping or pressure time decay. So this would be an indication right now. And if I went over here to change the effort to simply show that the patient is having a worsening effort, ignore this because, all right, so here's the mandatory breath. Here's the breath of the patient. See this big scooping out of this pressure time curve? You would be surprised that after watching today, if you go back to your ICU units and you're using volume ventilation, how often this actually occurs because you don't have the tidal volume or the peak flow set correctly. Now, I didn't need a ventilator to show this to you. I had a laptop and I had a projector screen, and you're going to get to walk away and go, wow, by virtually watching a simulator recreate a real life situation, I can go back and tactily go up to the ventilator and make the necessary adjustments with this. So again, simulation training is incredibly beneficial to enhancing the learning and the recall of the end user when it comes to manipulating a ventilator and so forth. With DHAB, I kind of went over and just showed some functional parts and try to make it a learning session for you guys. Like, hey, if you're not used to waveforms, you get a sense of what a waveform change looks like when you change the patient interaction. But are there any last things that you want to show that maybe I didn't cover in respect of time?
No, that's great, David. Thank you. There is a lot, of course, and of course you can play with the different modes. This is volume control. You can switch it to pressure control and see like what does effort would change. And so the possibilities are endless. But if you are an educator or you just a geek who wants to play, I used to play with this in the ventilator at 2, 3 o'clock in the morning, playing on this, and I was like, and it started beeping and I was just like, oh my God, what did I do? People complain around me. I think it's really good for education, and I wanted to show you the volumetric capnometry, but it's not in here too. So.
All right, thank you guys very much. Any questions for me and EHAB by chance?